Hello everyone, welcome to PCT Lecture 4. Today we discuss about transmission line model, capacitance. The capacitance between the conductors in a transmission line with constant permittivity epsilon can be obtained by determining the followings. The electric field intensity E from Gauss' law, and then extract the voltage between the conductors. The capacitance is defined by this formula, the Q, the charge Q, over the voltage. So let's start with a two-wire conductor or single-phase transmission line. The two-wire has a radius RA and RB, and the distance between them is D. First, we calculate the electric intensity, electrical field intensity here between them, and then integrate them to find the voltage. And then using this formula C equal Q over V, we can extract the capacitance between line A and line B. The detail is given in the textbook and also the lecture notes. In the end, we obtain this formula: C equal 2 pi epsilon 0 over logarithm of D square over RA times RB. In case RA equal RB equal R, this formula becomes CAB equal pi epsilon over logarithm of D over R. So we just talk about the capacitance between two lines. Now we imagine that there is a neutral line between the two conductors. The capacitance between the first line to the neutral is CAN or CAG, and the second to the neutral is CBG or CBN. Assume that they are equal. So the equivalent capacitance here will equal to the two new capacitance in series, and therefore the two new capacitance CAN and CBN, they are equal and equal twice the amount of CAB, or they are 2 pi epsilon 0 over logarithm of D over R. Next, we define the charging current, which is the current associated with the capacitance of a line. For single phase circuits, I charge equals J omega CAB VAB, or VAB over the impedance Z capacitance. For three phase, and in case it's balanced, the charging current equal the J omega C to neutral times VAN, or the phase voltage. In other words, the charging current caused by the alternative charging and discharging of the line due to an AC voltage. And this charging current will cause unbalance between the sending current and the receiving current. Next, we discuss about the capacitance of a three-phase line. So we consider the general case that we have the same voltage magnitude between the phases, and we assume a balanced system so that the total amount of charge equals 0. The conductors has different radius RA, RB, and RC, but now we assume that they equal R, and the effect to the earth is neglected. In this case, the capacitance of each line, they are not the same, but if we apply the transposition like this, then we can conclude that all capacitance in every phase they will be equal, and the average will be given by this formula again. Cn equal 2 pi epsilon 0 over logarithm of GMD over R farad per meter, where GMD is the geometric mean distance and it is the root of the distance between 1 2 times distance between 2 3 and times distance between 3 1. So in case that we have bundle conductors, we need to change the R into GMR or geometric mean radius, and in case of two strand bundle, the GMR equal the square root of R times D. In case of three bundle, the GMR will be square of R times D square. And in case of four strand bundle, it could be given by this formula: GMR equal 1.09 square of R times D cubic. So basically, it looks quite similar with the formula of calculating inductance. However, the GMR here is associated with the real radius of the cable, and that's the main difference. Now we look at the case of double line circuit. We apply the same formula. In this case, Cn equal 2 pi epsilon 0 over logarithm of GMD over GMR C. In this case, when the double circuit line is transposed, so that the average capacitance on each phase will be the same. In this case, the GMD and GMRC is given by these formulas, with the GMD equal the average of DAB, DBC, and DCAC. They are the distances between the single phases. So let's have a look at DAB. That is the average distance between phase A and phase B, which consisting of A, A prime, B, B prime. So as a result, the average distance is given by the distance between AB, AB prime, A prime B, and A prime B prime, and take the average. The same apply for phase B and C and A and C. How about the GMR? The GMR C here, C stands for capacitance, so that we know that it's different with the GMR L, which has the factor of 0.7788. But here we don't have that, so we put C here to remind us. Is the average distance is the average radius of phase A, phase B, and phase C. In this case, we can notice that the the bundle line, look like a bundle of two strands. So RA will be square root of the bundle radius RB times the distance between A and A prime, A prime. The same apply for RB and the same apply for RC. So we have been talking about the calculating of capacitance from a line to neutral without the effect of earth. When we take the earth into account like this, we need to mirror the whole system via the earth's surface. So when we do this, we have new distances from phase A to the mirror of itself. H1 here, phase B to the mirror of itself is h2, and phase C to the middle of itself is h3. Other than that, we have the distance between phase A and phase B, which is A B prime, which is also equal to A prime B. So we call them H12. Distance between phase B to phase C prime and phase C to phase B prime, they're all the same, and we call them H23. And finally, C to A prime or C prime to A, we call them H13. So the new formula will be given by Cn equal 2 pi epsilon 0 over logarithm of GMD over GMR or RB, then minus logarithm of the average distance of H12, H23 and H31 over the average distance between H1 and H2 and H3. So as a result, we see that the overall capacitance will be bigger. So for the homework, you will need to practice what we just discussed in tutorial 4. In the meanwhile, you need to prepare for lab 2 and the pre-lab will be marked. So please do come prepare and do not come late. See you.